Okay, guys. So arithmetic for computers, basically there are operations on integers, which we know already, addition and subtraction. There are multiplication and division, dealing with overflow, these things. Then we'll be discussing the floating point, real numbers, their representation and operations, inshallah. So starting with the multiplication, girls. So the multiplication is basically going back to, you have to go back to the high school and just try to understand how basically we need to multiply two numbers, the process which we can see here. So starting with a long multiplication approach, first we need to know each number, what we call. So we are having two numbers which we want to multiply, basically the first one and the second one. The first number, the one whom you are multiplying, is called the multiplicand. The another one by which you are multiplying, it is called the multiplier. Okay, and the process is very simple while it is in binary, basically. For example, now this is 1. Okay, then we have to check the multiplier least significant bit or the rightmost bit, and we check if it is 1, we need to multiply by this multiplicand, and you can see when it is 1, the complete multiplicand will copy here. You can see this one, right? This is like that. When what next? Then after that we will check the next bit of this multiplier. If it is 0, girls, simply we have to shift left and then just use here 0 0 0, yani because of when you multiply 0 with any number, definitely you are going to have a 0. Next bit again 0, and we have to shift one more space and we'll be getting this is again 0 0 0. Okay, then the fourth time shift 1 2 3 shiftings are there. Then girls, again here this bit is gonna be 1, and when we multiply this with that number, so multiplicand will copy exactly here. Now the next is last step is we are getting result as a product, and we need to add all these 4 rows, okay, together, then we'll be getting here. So girls, there is a point like we are adding 0 0 here, so adding 0 with any number is not going to help us. So what do we do here? Actually, we'll be looking, you see this, what do we call this one, flow chart, how we are going to perform multiplication. So here is one more point which we need to keep in mind, like the product, like the final result. The final result is basically, girls, the sum of the operands. Like if it is 4 4 8 bits, so product will be the double of it. If it is multiplicand 4 bit, so the product or the final result will be the maximum could be double, 8 bit long. Now just go through this flow chart, girls. So just starting with the we are starting here, and then we have to check the multiplier 0 bit, this rightmost bit. Okay, if it is 1, girls, what we will do, add multiplicand to the product. What we are doing here, first we are saying product is equal to 0, initial value of the product, like we are putting here as a 0, and the multiplicand is here, so add multiplicand to the product and place the result in the product. So next step is what? Product is equal to product plus multiplicand, multiplicand capital M I'm using, like that. So this is what we have to do if the right bit of this multiplier is 1. Next, after, girls, shift the multiplicand right 1 bit. So we are going to shift the multiplicand right, shift the multiplicand right left 1 bit. So it is gonna be shift 1 place right, basically. Then the shift multiplier right 1 bit, multiplier need to be shift right 1 bit. Why we are shifting the multiplier? We are because the multiplicand is shifting here. You can see this is here 1 2 3, third step again we are shifting this one. About the multiplier shifting, because we have to check the next bit whether it is 0 or 1. If it is 1, then we will be shifting one more time. If it is 0, we will be we can skip the shifting because we are interested to add this value with this value rather than adding with the 0. So this is what we are doing here, and this has to be repeated 32 repetition, because the number which is stored inside the register is 32 bit long. If it is not 32 repetition, keep on doing the same thing again and again and again. This is like that. Okay, things will be clear when I will give you example. by considering some numbers, and inshallah I will explain. So that will be more clear at that time. So that, girls, this is the hardware basically, which will basically implement the actual process. So here you can see we have a multiplicand, and the multiplicand size is 64-bit. The reason is that we are shifting multiplicand right with every, see here, we are shifting multiplicand 1 bit. And how many times we have to shift this? We know that 32 times. It means is that 32-bit is already there, is the size is 32-bit long, and we are shifting right. So we need at least 64-bit to fit the multiplicand. This is for that. Now girls, ALU. ALU again going to add this multiplicand and the product, which we say that initially it is 0. So product value is initially 0. So it is gonna be added with multiplicand and then producing this result here. Then the multiplier is shifting towards the right. So the multiplier, basically we are shifting towards the right, and we are not caring about all bits. What we are caring about by shifting, we are just testing the multiplier rightmost bit. So for that 32-bit is sufficient, because we are going to shift it and going to check the rightmost bit of the multiplier. And if it is 0 or 1, based on that, control test will be generated, and this control signal, for example, now let me give you an example. If the multiplier bit is, for example, 1, so this signal will be active. If it is active, so control will do what? Based on that multiplicand, what it will do? It will add the product, yani this will be there and this value will be there, and here this control signal will go there, the ALU will be activated and will add to this multiplicand and the product. And also it will generate the right signal, so it will save the result as a product, which is mentioned here. Okay, next is, after that, next step, it will generate the signal for the multiplicand to shift the 1 bit by left. This is one thing. So once this step, then this step. Then the third step is shift right the multiplier. So again, one signal, it is going here to shift right 1 place. This is how this this way this hardware will be working basically. Now moving towards basically the actual example. Now please check this one, girls. So here we have example. We are going to multiply 2 with 10, decimal 2 with 10, and if we write these things in binary, it is gonna big, and we are representing by using 4-bit so that we can easily understand the process. So saying 4-bit of the multiplicand and the multiplier, what should be the value of the product, girls? What should be the value of the product?
6. 8.
8. Absolutely right. It is gonna be 8, because as we said, it is gonna be double. So you can check here the product size. See, it is product size, and initially, as I said, it is gonna be 0. So this is the first initial values. So product value is 0, as you can see, and multiplicand is gonna be placed in a 64-bit, as I said, because it is going to be shift right places. So see, this is the multiplicand. Multiplicand yani this value 2. So it is fit in double size again, because it is going to be shift left side with every iteration. Next is multiplier, girls. So this is the multiplier, which is here. Now, so it is the initialization, right? Now we are starting the iteration, the first iteration. So here it is started like that. So first it will check what? The first rightmost bit of the multiplier. You can check it. It is 1. Okay, when it is 1, what should we do? We have to do first step, which is product is equal to product plus multiplicand. And what is the product value? The product value is 0. And what is the value of multiplicand? You can check here 2. So 2, I'm just saying in decimal, right? So this is like 2 plus 0. 2 plus 0 is gonna be 2. So the blue ones which is there, this is basically updating. Okay, the blue color. So it is now updated. So product is basically now updated. Its value become 2 now. Okay, so this is the first step. The second step is that the left shift multiplicand. So this time this blue line is saying that left shift the multiplicand. So when you shift towards left, what will happen? This one will be here and 0 will insert from here. So this is the shifting. So second step. The third step is that shift right multiplier. So this is the time to shift the multiplier, because we have deal with this one bit. Now we have to check the next bit of the multiplier. So we need to shift right, and we are not caring whether the bit is going to be drop or not, because we need just what is the right bit. So we shifted right. So we are having this one now. Okay. So this is what this will be updated now. Now, so this is this way first iteration finish. Second iteration again, check the rightmost bit. So this time is again 1. So if it is 1, what we have to do? Product is equal to product plus multiplicand. Again, so product is here. You can see 2 in decimal. So 2 and plus 4. This is the 4, right? So 4 plus 2, it will make 6. So here product will update as a 6, we can see here, right girls? So one step finish. Second step, shift left multiplicand. So again, the multiplicand which was here, it is going to be shift one more time here, which we can see here. And next step, we are shifting the multiplier right. So now this time multiplier is shifted. Okay. Now what next? Third iteration. We reach to the third iteration. Here we'll check the rightmost bit of the multipliers is 0. And we have seen, girls, as per the flow chart, that if this is right, we don't need to update the product, but we need to shift the multiplicand right, that's why no updation in the product, but multiplicand will shift right. So it is the multiplicand shift in the right, then shift right multiplier again and again, because it's become 0. So next iteration, the final iteration, because now the 0 which was start entering, see this one, after 4 shift, it reached to basically, here. So one shift, then second shift, then the third shift, and the fourth shift, it will be there. So after that, it's check again, it is 0. So again, no change anywhere here. But next time we need to shift the multiplicand. This is the multiplicand shift, and this is the right shift of the multiplier. So the final result is gonna be stored here basically in the product, as I said. So can you read this? Read out which value is this in decimal?
6.
6, right? And if you multiply 2 by 3, we'll be getting 6.
Yes.
Correct? Easy. So this is the way, this is the algorithm, in order to perform the multiplication. For us, it's so simple, we people use just a command, MUL, or we use just, the basic commands, other language, and it is going to be multiplied. But actual hardware, is there, and how it is working this way. So I can give you an example, I can give you table, and I can ask you, just update. So like that. So if it is clear to you, inshallah, you can easily update the table, the steps you can mention. Okay. So, one more thing, guys. We have seen that, in computer system, everything, the operations, or what we call hardware, they are synchronized. How they are synchronized? In order to synchronize, there is a clock. That clock basically synchronizes all the operations. Yani, anyone cannot do anything without synchronization. If there is a signal, if there is a clock, then only it will be working, and it will be working. The what you call component will be working only for the duration for the clock. Then it will assign to another one, something like that. So as we have seen that, girls, while we are updating this, we are updating this one. So you can see that we need to shift the multiplicand in the second cycle. For example, it is one step, yani one cycle is required. It is again second cycle, we are doing this one, and the third cycle we are doing this thing. So girls, while we are updating the product, after updating this one, can't we do these things in the same time? Yani shifting of the multiplicand left side or multiplier right side, we can do parallelly. If we can do it parallelly, we can optimize the operation. Otherwise, you can see how many cycles are required, because each iteration is requiring 3 steps. Means is that we have to spend 4 multiplied by 3, 12 clock cycles in order to just multiply 4-bit number. It is now 32-bit. So 32 multiplied by 3. So it is gonna be 96 clock time. Yani this much of time we have to wait in order to get the final result in the product. Are you getting my point?
Yes.
Okay, so how can we optimize this process or this hardware? We can do it if we can do this shifting, one time, one clock cycle, or what you call parallelly or simultaneously. If it is possible, then we can optimize the process. So see now. So here is the optimized multiplier, girls. Here, the two things are happening simultaneously, which is like shifting right here. Okay, so shift right is doing in parallel. So perform step in parallel. Yani addition, when it is performing addition, will be also looking at the shifting step. This is something like that. So it is showing here shift right is there and this one is there. So optimization is possible like that. So one cycle per partial product addition, that's okay if frequency of multiplication is low. Okay, what you need to understand here basically, we are now performing two steps in parallel like addition and shifting, so that it will, the overall process will take less number of clock cycles and we will be having result faster than the one without parallel basically. Okay, one more thing which is possible, girls, this is the more faster multiplier. In order to have this much of faster multiplier, what we are having, see, uses multiple adders. Rather than just using a single adder, we are using here multiple adders. And how many adders we are using, you can check it. Like this is, adding 2 bits, bit by bit actually, it is bit by bit addition, next bit by bit addition, next bit by bit addition. So this way we need at the top level, 30 to 32, then next, then next. So we'll be having many adders, but what is the advantage of it? Because they are working in parallel, so it is going to be very fast. But there is a cost performance trade-off. What do you looking for? Do you need a very high performance regardless of the cost? All right, then you can go for this hardware. But yeah, you need some cost effective hardware. So you can compromise, you can compromise with the performance somehow, so you can go for it. So here is a trade-off basically what you need basically. So can we pipeline several multiplication performed in parallel? So this is what we are having basically, just to let you know. And we have options, but again there is a trade-off. What do you want, performance or cost? What is important for you? Okay, now coming to the point, girls, which we have seen already, these instructions, and hope you have used these instructions, which is like MULTS, MULT multi, and here. So now there are two 32-bit registers for the product. And what are the registers? There is a high register, another one is a low register. Do you remember when I start this chapter number 2, then when we are discussing the architecture of the MIPS, then I told you there is a separate hardware and what you call separate unit for multiplication and division. Do you remember? Or should I show you that? If you not remember, maybe it is there in the beginning or of that chapter number 2. Give me a moment. I can show you
it's
that.
in the beginning of chapter 2.
Chapter 2, huh? Okay, let me share it with you. See, can you see this now? See, so here we have ALU, but integer integer multiplication division. We have some different type of arrangement for it, and the result is high and low. Yani for integer we have separate high and low registers, and both registers are of 32-bit long. Both are 32-bit long. Okay. Now go back to the main slide. Where is that? Screen chapter 3. Okay, guys. Can you see the chapter 3 now?
Yes.
Okay. This is the chapter 3, guys. So here for the multiplication, as I said, there are two 32-bit registers for the product. So product, we have high, where the most significant 32-bit is gonna be stored. Then LO, least significant 32 bits are gonna be stored there. Okay, And how it works, girls, see the MIPS instruction, MULT, okay, and here we are providing both multiplicand and the multiplier, and it will multiply together. Girls, can you see, is there any destination here? In this, there's no destination.
No.
Only two sources, right? Only two sources. So where is the destination? By default, the destination is high and low registers. So the result is 64-bit, which is gonna be stored in high and low. Okay. Similarly, we have MULT unsigned. It is also work the same way, but it is for unsigned numbers. Now, girls, after that, we just give two numbers and results where it is. The result is in low and high. So usually we are not multiplying very high number. If we are multiplying very high number, so we can check the high value register in order to check is there any overflow greater than 32-bit. Yani I can check the value of the HI. If it is greater than 1, it means is that the result cannot be fit in LO and it is now extended to the HI. So we can check it. But if your numbers which you are supplying here, for example, in the previous case, that was 2 and 3. So when you are multiplying, your result is 6, which is basically going to be stored inside the low register, right? Because to store the 6, value 6, a low is sufficient. We don't need to use the HI. So we know that once the result is ready, we need to use another instruction, which is MFHI or MFLO. What is that one? This is move from high or move from low. Where to move? The destination register. Now you can use any register, T0, T1 or S0, S1 in order to check the result. So you need from LO, we know that because 6 will be stored there. So I will be using this instruction and I can specify any register. So the result will be available there. Okay. So this is like move from high and low. You can test high value to see if the product overflow 32-bit. We can also check this one. Is it clear, guys? And now what is happening basically, you people did not use this MULT or MULF, but what you use in the lab, if you remember, did you use MUL? Just multiply? MUL?
Yes.
Right? And it is a pseudo instruction, by the way, and it is offered by the assembler. And how it is gonna be break? It is going to be break into two parts, which we have discussed. The one is MULT, this one, girls, and the second one is this one. See this one? So the result will be stored like that. So this instruction is equivalent to two instructions. What are the two instructions? I am just going to highlight. This is the one instruction, and this is the another instructions. So this instruction MUL RD, RS RT comprises of two instructions, which is like that. Okay, so this way, what we will be having in RD, girls, we will be having in RD the least significant 32-bit of the product, which is in RD. Is it clear to all of you, this explanation?
Yes.
Clear. Okay, this is the way how it is working. So we can simply say this pseudo instruction is equivalent to two MIPS actual instructions, MULT RS RT, MFLO RD. All right. So you can check it, girls, when you are going to have a lab and try to use this MUL instructions. After assembling, you can check there how this pseudo instruction is going to be translated into the actual instructions. Okay. All right. Next is, girls, division. So division is again better to know what are which number is this, what is that places. So just have a quick look. So we are going to divide this number with that number. We say like that. So this number by which you are dividing is called divisor. The number to which you are going to divide is called dividend. When you start dividing, girls, we receive basically quotients as a result. Am I right? And we also receive the remainder as a result. Okay, girls. So here you know that you first, whenever you are dividing, we have to make sure that divisor should be greater than 0. If it is 0, what will happen? the division result is going to be infinity. We know that if you divide 0 with any number by 0, it is going to be infinity. So we have to check that one. Okay. Then it is a long division approach, which is like if divisor is less than dividend, we will be checking. Then 1 bit of quotient is going to be subtracted. Otherwise, 0 bit of the quotient. This one, restoring the division sign. So there are 1, 2, 3 steps which we have to perform. See, you will understand this step with an example. So better rather than you can read it, but how it is going to be implemented, I am going to show you with the real example. Before that, we can also have a look on the division hardware, girls, and the flow chart, and see the flow chart. It is like starting from here. What we do in the beginning. First of all, there are some initialization which is not mentioned maybe here in the flow chart, but it is mentioned in the example. I'll show you there. So what we have to do first, subtract the divisor register from the remainder register. And remainder register is actually initially value will be put there at a 0. When we subtract a divisor from the 0, definitely we will be getting a number as a negative, because subtracting some number from 0, we will be getting a negative number. So negative number, yani will be testing the rightmost bit, whether it is negative or positive. It's like that. If it is negative, yani remainder answer, because we are updating the remainder, by the way. Subtract divisor register from the remainder register and place the result in the remainder. So if remainder is negative, it means is that the divisor is positive, yani greater than this. So if this is 0, then we have to restore this one, which is here corresponding to restoring. And if it is greater than 0, we have to shift this way. And then this one step. And by the way, because of one additional iteration is required there, it is because of we are just subtracting without looking whether the divisor is greater than 0 or not. So we have to compensate this with the restoring one extra step, which that's why here we are having 33 repetition. Yani if the size of the number is 32-bit long, we have to iterate 33 times. Yani the size of the register plus one extra. The reason is that because we are starting with the subtraction, we have to restore if this subtraction answer is negative. Okay, you will understand with an example. Just wait for a moment. This is the hardware, girls. So divisor is placed here. Divisor is placed with a 64 bits long. Initially it is 32-bit, but we make it 32-bit. Why? 64-bit. Why? Because we are going to shift right. Quotient will be same, 32-bit long. It is going to be shift left, right. And this is 64-bit ALU, which is adding the remainder plus this one. And this is the control test. Initial dividend value will be placed here. So now we can see with an example how this hardware is basically working. Let's move with an example. So the example is, girls, we are trying to divide 7 by 2. Okay, in tens, in decimal. So we can write its equivalent value in basically binary, which is like 7 in 4 bits, 2 in 4 bits. Girls, I told you the iteration will be, because the size of the number is 4-bit long. So how many times I have to iterate, repeat this step? As I said, size plus 1. Am I right? Size of the register plus 1 extra. So iteration will be 4 times, 4 plus 1, yani 5 times, which is like that. Now see here. So initial step. Initially, quotient is 0, 4-bit long. But the divisor, who is the divisor? This is the divisor, right? 10, yani 0010, which is 2. It is going to be placed like that. It is placed in the high 4 bytes and the lower 4 bytes will be as it is. The reason, because we are going to shift it towards right. This is the reason. Okay, guys. Then remainder. How this remainder is going to be set? As I said, what is the remainder? Initial remainder will be set with this dividend. Initial value will be equivalent to the dividend. Okay, so dividend is here, which is 7, and place in double bits, which is like 8, because it is going to be shifted rightward, like that. Now starting with the first iteration. In the first iteration, as I said, very first thing, you need to update the remainder like at remainder minus divisor, remainder minus divisor. So remainder is already having dividend there. So dividend value, if you just read in what you can read it in decimal. Which value is this? 7. Am I right? 7. And yes, 7. 111. And what we are doing here? Remainder minus dividend, divisor. And divisor value is, you can see, it is like, it is greater than 7 or not, if you just read it.
Yes.
Yeah, because with the weighted method, 1, 2, 4, 8, 16, 32. By the way, it is 32 now. So when we subtract remainder and when we division from the remainder, definitely the result is gonna be negative. So here we are getting the result here, which is blue updated. Okay, so result is placed here. Yani remainder is updated now. So what does it mean, girls, after getting this result? This is saying that the subtraction result is negative. It means divisor actual is greater than the dividend. So we can go one time. So what we will do, we will check here that the remainder is less than 0. Yes, it is less than 0 because it is negative. So in this case, we have to adjust the remainder. How I will be adjusting this one? The one which I subtracted earlier, I am going to add it early again so that the remainder will be adjusted. So we subtracted divisor from the remainder. Now we will be adding divisor to the remainder, and it is now gonna be what you call restore. This is now restore. This step side by side. Because the result was negative, yani the remainder is less than 0. Now we will check Q0 is equal to yani shift SLL, shift logic left logical Q. What is Q? The quotient. So we will shift here one step, and we this way you can see here. Okay, so next is what? Shift divisor right. The time to shift the divisor right. It is shifted left side and fill the 0. You can see here. And any Q0 should be 0. We will be filling like that. So this is the placed bit. Now next step is shift dividend right. So you shift the dividend right. Yani this one is gonna be shifted right now. So this is one iteration. This is gonna be again next time. Here again, girls, what do? We again do remainder minus divisor. Divisor value now you can say is less than that. Earlier it was 32. Now it is I think 16, right? It is 16 now. So we are trying to subtract this from the 7. So 7 minus 16 produce this result. Okay, which is updated. In second step, we'll check remainder is less than 0. Is this less than 0? Can we check it?
Yes.
Is it less than 0, right? If it is less than 0, restore the remainder by re-adding that one, and we will be restoring, and shift left logical and place the 0 bit there. So this is one more 0 answered here, and it is shifted. And the third is shift right the division. So division is again shifted here. You can see now it's become 8, and we have here in the second step. Third step again, girls. Third is iteration, not the step. Here again, we subtract divisor from the remainder, girls. And because it's 8, it's 7. So again, this time we will update it. And the second step, we check remainder is less than 0. Yes, it is still less than 0. If less than 0, adjust the remainder to its original value, which is like that. And shift left logical and 0 insert. So same thing is here we have to do. Shift right this one. So now, girls, you can see the divisor become now 4, which is less than the remainder what we are having. So fourth iteration, girls, which is now the different. Please focus here. So we will do again the same thing. We will subtract it and we will be getting the result as a positive. The reason is that we are subtracting 7 minus 4. So that's why this result is positive this time. We'll check remainder is greater than 0, equal to 0, greater than 0. Yes, if it is the case, then we shift the quotient left side, but this time the bit which we are inserting from the left side, this is basically the 1. The reason is that the result is positive. So the entered value which we were entering from this side is going to be 1 this time. Then shift divisor right side. So we will be shifting one more side. It's now become 4. Now, fifth iteration, we'll do it again. We'll subtract it and we'll find it. Again, the result is 0. Yani remainder is greater than equal to 0. If this is the case, what do we do? I just explained to you. We'll shift the quotient and place the 1 again one more time. Yani insert the 1 from the left side. So we will be having like 0, 0, 0, 1, 1. Now shift the divisor right side, and this is the shifted here. Now girls, final answer, yani what we are having remainder here, and we are having quotient here. These are two my answers. We need to verify this one now, girls. Okay, we can verify. In order to verify, just look here. We are dividing 7. Basically, I'm just writing in decimal 7, and we are dividing by 2. So, girls, how many times this 2 will go in 7? 3 times. 3 times. It is gonna be 6, and remainder is 1. Correct? Remainder is 1, and this is the quotient. If I write quotient in binary, will it be like 0, 0, 1, 1, girls? By using 4. What about the remainder? If I write again by using 4-bit, 0, 0, 0,
1.
1. Now can you verify this one with this one, remainder?
Yes.
And this quotient with this quotient? Correct? Clear? So these are the steps which basically hardware is going to perform to divide two 4-bit numbers only. Think about the 32-bit long numbers division. That's why we need to deal this one separately. We cannot just use addition and subtraction hardware. We have to have a different hardware for it. Okay. So again, guys, in order to optimize this process, there are some things which we can do parallelly, as I explained to you. Like while we are subtracting this thing, we can also perform the shifting operations parallelly. Okay, which is that. The next thing is the optimized, the divider. So here, what is the optimization? Yani when it is performing addition, at that time shifting right of the what was that? Divisor, and shifting left of the quotient will be happening parallelly. So this way we can save the time and we can make the process fast. One cycle per partial remainder subtraction look a lot like a multiplier. Same hardware can be used for both. So it is like look like the same hardware which you can see, because shifting and adding, it's there, 4-bit 32-bit add and shifting. So it look like the same hardware which we use for the multiplication, because it is what? Shifting addition, shift and addition process. So same hardware which we use for the multiplier can be used for the divider basically. This is something. So this is all about the divider, but here we don't have any faster divider. The reason is that, girls, sorry, just a minute. The reason not to having faster this division is that because addition is basically, or re-addition is depending upon the previous subtraction operation. Yani once we are subtracting divisor from the remainder, we need to check whether the result is less than 0 or greater than equal to 0. Then we restore it. That's why we cannot have a fast division which can perform, which we can perform with many adder or many adder having multiple adder which can add individual bits together. So can't use a parallel hardware as a multiplier. Subtraction is conditional, because subtraction is conditional on sign of the remainder. Okay, we know that one. And the faster divider is the SRT division. Basically generate a multiple quotients bit per step, it still require multiple steps. So there is no faster division possible. There is some way which is possible, but it is still required multiple steps. This is something. So it is about faster division. And again, now coming to the actual instructions, girls, which we have corresponding to the division. Here again, high and low registers are in use. High consists of the remainder, girls. Low consists of the quotient. And what is the actual instruction? This is a div. which perform RS minus RT. Here is the dividend, here is the divisor. This is for the unsigned. And girls, in this case, in this instruction, actually, there is no overflow or divide by zero checking. Yani you can also place here a zero, but what you will be getting, there will be error, but there is no like a testing which can, tell you, okay, no, you cannot do it because it is a zero. So testing is not there. This is something. So there must be a software which you have to check before supplying in the RT value, whether it is zero or greater than zero. Then girls, the result will be stored in high and low, and then we have to use MFHI or MFLO to access the result. Which results you want? Are you going to check the remainder? Are you going to use the quotient? Are you getting my point? This is something. So based on that, inshallah, you are having a lab. I think that this is the last lab of the programming, where you will be learning about multiplication and division methods. Yes, I think, yeah, there is one more lab based on that. Okay. So we have done with this way, and now there's a floating point arithmetic. So girls, here we can have a break before starting this new topic. All right, girls. So the second important topic of this chapter is floating point. So representing for non-integer number. So we have discussed about the non-integer. Integer is so simple to store. We know that one. Just convert an integer given decimal into binary and then store it. But girls, think about a very large or very small numbers. Okay. So including very small and very large numbers, like we are having this number which is very small. Like we have 0, 1, 2, 3, and 10 zeros after the decimal. Then we have this number 5. Okay. And girls, if I ask you just convert into the binary, you know the process, how it is going to be converted. Just keep multiplying this fraction part by the 2 and keep noting the basically the integer part. So girls, in order to represent this number, we must require a lot of binary bits to store this number, to convert into the binary number. Once converted, then we are going to store in the memory. So memory is going to take a lot of bit in order to store this small number. What if we convert this number like that? We represent this number like that in floating point. So like 0.5 multiply by 10's power minus 10. Because of we have 10 zeros, I just placed 10 zeros so that we can see this is minus 10. So girls, if I ask you, just save, for example, this number. So it will take less digit. If I ask you save this number, it will take very less digits. Similarly, if we have this larger number with again 10 zeros after the 5, so we can represent this number like that. Okay, but if I convert this one in binary, it is going to have a lot of binary bits, and then we need a lot of memory location to store this number. What if I convert it like that? It is after normalization or after converting into scientific notation. So girls, if I ask you, okay, this is 5, just convert it into binary. So how many bits I need to represent this number in binary? Is it gonna be like 0, 1, 0? 3 bits, and we will be saving its what we call this one exponent part. This part is called fraction part. So exponent represent 10. How many bits I need to represent that 10? It is gonna be 1, 0, 1, 0. Are you getting my point? This is 4-bit. This is just 5 bits, and we can save this larger number in the memory with very less number of binary bits or bits, right? This is the way. That's why understanding the floating point is very important, and conversion to the floating point and then saving the number accordingly is very important. So now, like scientific notations, guys, we have discussed this how to represent in scientific notation. Do you remember the scientific notation? We need to place the decimal point just after very non-zero bit. Do you remember the very non-zero number? We need to place the decimal point in order to convert the scientific notation. Then we have this one. And we call this one basically normalized. This is now normalized. Similarly, they are not normalized. because we have to shift the decimal point, and decimal point must be just after the very first non-zero digit. Yani it is not the correct representation, and this is not the normalized representation. So in case of binary, how this representation look like? In case of binary, girls, we'll be having like plus minus number, and one bit will be there. It will always be one or not if it is a binary number. If it is non-zero, will it be always one? It cannot be 2, 3, 4, 5 in case of binary. It will always be 1. Then we'll be having 1 point something. So girls, because it is gonna be all the time 1, so we are not going to save this 1. It is gonna be considered as a implicit. It is there. We will be saying like that. So and x is the basically the fraction part, or what we call significant, we are going to store in the memory by this exponent, which is represented by the y by y. So I will explain why we don't need this 1, because of it is implicit and we don't need to save it. We'll be considering that the 1 is there and will be considered while we are converting the number. So girls, hope you remember the float and the double in C. Do you remember these data types, right? So float, how much size of the variable if we have this float type of variable? What is the size of the float variable? Remember, it takes basically 4 bytes. Then we have double, it takes 8 bytes long, something like that. Okay, so we have this 2 representation. Now next thing is, it is about floating point standard, which we follows, basically our computer system follows. It is a IEEE standard 754, which is introduced in 1985. IEEE Institute for Electrical and Electronics Engineers, basically, and it produced basically given this define this state what we call representation in 1985. It is developed in response to the divergence of representations. There are a lot of representations. So just to respond, other than having a divergence representation, let's have a uniform representation of a floating point numbers. So portable issues for the scientific code because of it. Now almost universally adopted. There are 2 representation. There are 2 ways. One is called single precision, which is 32-bit long. Another one is double precision, which is 64-bit long representation. We'll be discussing both the representation, both the standards one by one, or let's see now what is this. So IEEE floating point format. What is that? This is a 32-bit single precision format. And you can see the fields here. So out of 32 bits, girls, 1 bit is reserved for the sign bit. Okay, it will represent the sign of the number, whether the number you are storing is negative or positive. Then next thing is the exponent. Okay, it requires 8 bit to basically store the exponent. Then the fraction part or significant part, which requires 23 bits to store the fraction part. Similarly, these things is gonna be double in the fraction, in the double precision, then 64-bit precision. So sign bit is same. Exponent will increase from 8 to 11, which you can see here, 11 bits. And fraction part from 23, it reached to 52. Okay, so this is basically the single and double precision floating point format. Now, it is basically the actual number, how we are going to retrieve that actual number, or we are representing here. So this is the formula, -1s, s is the sign, then +1 is here. As I said to you, we never store the 1, which is the left of the decimal point, because it is implicit, it is always there. We just only store the fraction. So a fraction is going to be stored here rather than the 1, which we'll be adding later on while we are converting it. And we are going to have to use power exponent minus bias. So this exponent, while we are retrieving, yani we are retrieving from this format to this format, we'll be using this formula. So exponent, yani whatever is stored here in a E, we'll be using that, and we will be subtracting the bias. Now, what is the bias? The bias is for single precision is is already specified, which is 127 for single precision. And for double precision, its value is 1023, which you should memorize or remember, okay? Because we need to use subtract this one while we are converting from this floating point representation to the actual number, okay? And the thing is, what we need to do, as I said, it is implicit. So you can see this one. Significant is one stored. So this is 1 point is restored, and it is already there. We need to restore it. So always has a leading pre-bits 1 bit. So no need to represent it explicitly, which is basically the hidden bit. Which one I am talking about? This one. Okay. For example, if 4.5 we are having, we can represent this way. But this is not the correct IEEE representation. We have to make it normalized first. So in order to normalize it, the decimal point must be placed just after the very first non-zero digit, and it should be 1. Then we'll be placing here. So this is our fraction part, and this is our 2 is basically the exponent. Then we will be saying the significant, which we are going to consider, which we are going to save, is only 001. We will ignore this 1 because it is implicit. When we will be restoring, it will be considered there according to this formula, yani 1 plus the fraction part which we are getting back. So with an example, inshallah, then things will be clear to you. There are some limitations also in a single precision range, yani some bits are reserved, which cannot be there. So what are the reserved? The exponent field, which is like 8 bits, all are zeros and all are ones are reserved. Okay, it means is that what is the smallest value of the exponent? It will be 0.0000001. It cannot be all 0. So it means is that the actual exponent which is there, because it is representing 1 minus 127, yani this will be the smallest value in which is going to be stored there as a actual exponent. Okay, now another thing is that the fraction is basically can be all zeros. As I said, there is no problem for the reservation. It is only for exponent, but not for the fraction part. So here is like that. We can have this all zeros. Then if we have smallest positive number, girls, it can be represented like that. Small positive, yani S will be 0. E will be all 0 except the last bit should be 1, because this is the minimum possibility, and fraction could be all zeros. Similarly, the largest value as this is reserved all ones, so this will be the 1 less than that one. Okay, the actual exponent will be 254 minus 127, which we will be getting, plus 127, and which we can represent this way. And significant would be all ones, and this is the largest positive number which we can represent in single precision. Similarly, girls, same thing is applied to the double precision, like all 0, 0, 0, 0. And how many zeros are there? Because it's exponent. So 11 zeros, 11 ones will be like that. So minimum will be that. So this way we will be having actual exponent will be like that, because 1 is already reserved. So remaining is how much? Because I say 1023 we have total. So 1 less, yani 1023 we can have minimum as a smallest, and the fraction will be all zeros, and similarly for the largest. Now, going to discuss with actual, conversion with an example. Inshallah, things will be clear. Before that, just look for the precision, yani how accurately we can store or restore the information stored, which is like the relative precision. All fraction bits are significant, yani the bits which we are having, it is basically all are significant. Okay, so single approximation, in single representation we have approx 2's power 23. It means is that equivalent to something like that. It means 6 decimal digits of precision, yani the stored value can be stored a number within 6 decimal digits of precision. If we have a decimal number 5.0003, 6 places, up to that we can easily store inside by using single precision format. On the other hand, if it is a double precision format, as I said, because here the size which you are, 23 was the size, and here we have 53 for the exponent field, right? So here the precision is 16 decimal digit of precision. Yani the stored value with the double precision point is gonna be very high. It is more precisely stored and restored basically. So these are the 2 points which is mentioned here. Okay, 6 decimal in a single precision, and it is 16 in double precision. Okay. Now girls, let's have an example. So in this example, we have asked express minus 3.75 as floating point number using IEEE single precision. So it is given single precision, we have to express this number. Single precision, yani how long it will be? What is the size of the single precision? 32-bit. Am I right? 32-bit. Yes. So, what we need to do first, girls, we need to convert this 3.75 first, okay, into binary. Do you know how to convert it into binary? It's simple. So, let's first normalize as per IEEE rule. Okay, so how we will be doing? So, very first thing is to convert this number into binary. So here is the number minus 11.11, which is 3.75 in binary. Now check it. Is this normalized? No, because of the rule says the decimal should be after very first 1 bit. Okay, so what do we need to here this time? We need to shift this decimal point towards left. Towards left. How many places? 1 places. Girls, the rule says when you shift this decimal point towards left, the power of 2 will increase. Power of 2 because it is a binary. Okay, increase positively. So it is like 1.111 multiplied by 2's power 1. So here is the exponent now, which we have to store, and this is the fraction part. So as I said, now we need to find what is S. S is now 1 because of the number is negative. Am I right? Sign bit. Next, what we have next? Fraction. Fraction part. As I said, fraction is gonna be 111. Okay. Then what is the exponent, girls? So for the exponent, we need to find this way. The formula is exponent is equal to 1 plus bias. 1 plus bias. Okay, if you go back and just check the rule, what is that? Exponent minus bias. Exponent minus bias. So this is the way. Means what I have to write here? Exponent minus bias means exponent minus bias. And what is the value here? It is 1. What we need actually? We need exponent. So can I say exponent is equal to 1 plus bias, right? And what is the value of the bias for the single precision? I told you 127. For single, it is 127, correct? So it is gonna be 1 plus 127, which is 128. Okay, guys. And do you know how to write 128 in binary? Because everything we have to, it is a decimal, huh? We have to convert into binary. Do you remember the weighted method? 1, 2, 4, 8, 16, 32, 64, then 128. So an exponent field is basically 8-bit long. No, 23-bit long. Okay. So it is like exponent is gonna be 1, 0, 0, 0, 0, 0, 0, 0. Sorry, it is 8-bit long. Yes. Fraction is 32-bit long. So it is like that. So this is now converted. Yes, correct, Afifa. This is now. So now finally we have sign bit value. We have fraction value, or which is 111 only, but leading zeros will be there. And how many? Because fraction size is 23-bit long. this is 8-bit long, and this is 1 bit long. So time to fit all these things according to the format. So while we are going to fit this one in according to the format, see now what we'll be getting. This is your final answer. Single precision with 32-bit representation. Is it clear now? This is S, and this is what? Exponent. And what after exponent? This is fraction. Yes, correct. It is a fraction. So this is the representation. Clear to all of you? Understand easily? So this type of question may come and you have to do it like that. You can just show these things. Okay. Now girls, let's have one more example. It is a single precision. If I ask in double precision, what will be the changes, girls? Can you please tell me? If I ask in place of single, if I say girls, do it in double.
Exponent will be 12. Yeah, 11 bit.
Exponent will be 11 bit. Okay, it will be 11 bit. But what will be the formula in this case? Do you know? In double case, it will be 1 plus. Here you use 127. Yes, Fatima, absolutely right. 1023, which is 1024. And then you will be using 11 bits to write 1024. Okay, this is the way. So you will be writing 1, 2, 4, 8, 16, 32, then 64, 128, then after 128, 256, then 124. Yani 1 0 0 0 0 0 0 0 0 0 1 2 3 4 5 6 7 8 9 10. Are you getting the point? You know, this is the representation in by using 11 bits. So you will be storing something like that. Okay. And what about the fraction? Fraction, girls. Here I represented 23-bit long, right? 23. Then at that time it will be 1 1 1. And how many zeros will be there now? Can you tell me? This is the size of 52. No, Fever, this is 52-bit long. It is 23 for the single and 52 for the double. Go and check, see. Check. Fraction. Okay. 11 for the exponent. Getting point. So how many zeros will be there? It will be 49 zeros there. Yes, Fatima, absolutely right. Yeah, you don't need to write all 49 zeros. How can we represent the result at that time? We can just simply say, yani this much of zeros. I'll show you one more example, which will clear the point. Okay. Okay. Another example. So the very first step, normalized. Convert this decimal into binary. Okay. After that, we are getting this binary. It is not a normalized form. We need to shift decimal point towards right. While you are shifting decimal point towards right, the power of 2 will be increased negatively. Yani it will be 2's power 1. Now, girls, here we can note it down. The sign is 1. Fraction is 1. Why fraction is 1? Because you can see here it is the 1, right? It is 1 here. Next, what is the exponent? So fraction is 1 just after. And what is the exponent? The formula, right? 1. Okay. But see, Mariam, is this 1 or minus 1 this time? Right? Yeah, it should be minus 1 because you just noted down here. What is that? Then add the bias. Okay. So simple. We can have this one 8-bit. It is in single, right? If I ask you in double, we'll be having in place of 127, we need to use 1023, which will be like that. Yani 11 bits long. Hope it is clear, right? Yani I am showing both the things. If we ask in single, if we ask in double, hope it is clear to you. exponent. Now last thing is what? Fraction. So girls, fraction is 1 only. We have seen that. Okay, 1 only. Now time to represent. So see, this time you don't need to write the all 32 zeros, because this is 8-bit. Now this is 23 bits. So you can just show here what is blue means. Blue means the total size is 32 bits. What is the important here? This one, because we know that leadings are all zeros. So we can just show, okay, total is 32 bit. So this is up to here is all important, but then zeros are there. It is about single precision. What about the double precision? Same. We can see it is gonna be all information has to be there. Yani sign has to be clear, exponent has to be clear, then the fraction is the one has to be clear. Here are the leading zeros, which you can say, okay, 64 bits should be represented in this case. Is it clear to all of you girls? Any doubt, any question up to here?
Yes.
Clear to all. Okay, now girls, now just in these two examples we have seen how to store the decimal number into the memory, yani how to convert it into a floating point. Now girls, let's take it opposite. Yani I am going to give you this representation, and I'm asking you what this representation is representing a number. What is the number? It is represented like that. So what number is represented by the single precision floating? So the important thing is here single precision is mentioned. If it is mentioned, so things will be easy for us. Okay guys, so please start noting what is mentioned here. Sign bit is given, so I can easily say sign bit is 1. What is next one? This is exponent. Exponent, okay. Or the fraction, again we can see the fraction. So if, for example, if fraction is there, so we have like 0 0 blue color, right, and it is in 2. So girls, we need to convert. See, these are the all zeros. We can neglect this one, because the important thing, the very first non-zero digit, which is important. And girls, fraction, you know that it is yani decimal is already there. This is the fraction point, because 0.1 is restore, we know that. So 0.01, and you know what is 0.01? You can simply convert it, or if you remember the concept of weighted method, it is gonna be -1 after decimal, -2. Am I right? -1, -2, correct?
Yeah.
So
Yes.
because this is 0, we can leave it, but this is the 1. So 1 over 2's power 2, what it will be? 1 over 4. And it means, is this clear? Right? So this way you can convert, or you know how to convert very well, easily you can convert. But because of fraction, keep in mind it is a fraction, it's not an integer. Okay, it's a fraction. So we just convert it. So after conversion, we have this number, girls. Okay, fraction part. Now what else we have to look? We have to look now exponent part. So for the exponent part, we have given 100001, and we know that in 8-bit, if this is the highest one, which means 128, then which is the 1 here? The weight of this bit is 1. So 128 plus 1, yani it is representing 129. 129. So girls, time to restore with this formula. Time to restore the information with that formula. So here we just put x is equal to -1 and s is given to you, which is 1. Place here. And as I said, 1 is restored already, 1 point. So 1 is there, plus fraction. And what is the fraction? 0, 1. We will consider up to the non-zero bit, any 1 bit. So it is 0, 1, which is here 0, 1, which is in 2. Then multiply by, the formula is exponent minus bias. So exponent is how much is given? 129, then minus 127. So when you solve it, you will be getting that -1 is there, 1 plus 0.1 multiplied by 2's power 2. Okay, so girls, you can easily say -1 here, and 1 plus 0.1, it is basically 101, which is in 2. You can say like that. Okay, then what it is representing? minus 5.0, or what you can say simply, I think, yeah, it's okay to understand this way. Okay, is this clear to all of you now? Is this clear, guys? How to convert it? How we converted this one?
Yes.
Yes.
Right. So this way we know that this number which was here, this representation was showing for minus 5.0. This way we can have any number we can represent. Let's have one more example. Okay, I think it is clear. Like this is okay now. Not one more example. The next thing is about addition. It is about floating point addition. Next topic is floating point addition. Yani, how it is gonna be, perform addition when it is represented in floating point. So the rule is very simple. There are 4 steps which you have to mention. See this one. Step by step. To consider a 4-digit decimal example. We have this decimal example. This is one number. This is another number. We wanna perform here addition. I think you have already done these things, in electronics. So we need to perform this one. So in order to perform that one, guys, we have to align the decimal points in a way that the exponent parts become common, same. So for that, we'll choose the smallest exponent. So which one is the smallest exponent? The 1 or the 2? Number 1 or number 2? Number 2 is having the smallest exponent, which is minus 1, correct? So we have to adjust, we have to make it 10's power 1. So for that, we know, I just explained to you, if we shift the decimal point towards right, the power will increase positively. So if I shift one place, so one power will increment. When I increment by 1, it will become 10's power 0. I will shift one more place. When I place one more point, so it will become plus 1. So here is the point. Will not change this larger, but we shifted the decimal point towards left. So we will be having a common exponent here. After getting this one, this is the one step. Second step, add significance. We have to add the significance. Yani, add the fraction parts only. When you add it, you will be getting this answer, and this is your answer. This is the common fraction part. After that, third step is you will normalize result and check for overflow or underflow. So here is that. After that, we'll be checking that are we representing this way? We are representing this way, but it is not normalized because decimal has to be shift after 1 point. So we will be shifting this decimal towards right. And I said when you are shifting decimal towards left, it means the power will increase positively, which is like that. Next is that we need to round the renormalize if necessary. So rounding, yani we will be representing this one up to 3 decimal of places. Rounding, yani will be dropping that one. Do you remember round to even rule? If you are dropping 5, okay, will we check the bit, the retained digit has to be even. So now it will make 1.002, which is 10's power 2. This is like that. So this is the actual number, any answer after addition. One example of the addition. Is it clear, girls? Any doubt or clear to all of you?
Okay.
Okay, so here we perform decimal example. Let's have one binary example. So here we have a number 1, number 2, and again we will check their exponent part. If we need to align binary points, how will we be aligning that one? We check which is the smallest one. This is the smallest one, this one. So we will be shifting the decimal point towards, as I said, right, so that we can make minus 1. So I need to shift 1 point only, so that it will be 2's power 1. Now this is another number. So our second step is to add the significance, yani add the exponent part. We'll be adding that because of it's negative, so definitely it will perform a subtraction operation. This is the result, and this is the common exponent part. After that, third is normalize result and check the overflow. So this is the normalized result, girls. in order to normalize, decimal must be placed after the 1, yani 1, 2, 3 shifting. While we are shifting towards the right side, the power of 2 will increase negatively. Yani 3 place minus 1 was already there, and minus 3 will make it minus 4, and this is the result here. And with there is no overflow, there is no underflow. The reason, because the number is very short, and we can say this can easily represented by the value, because it's minus 4, and we can represent up to minus 126. We can easily represent. Okay, and this number is again on 3 bits. So it is. Then next is the rounding. So for the rounding, it is already 0, 0, 0. So no change is required, and this is also correct. But the result is in binary. We have to convert this one into decimal. So in order to convert into decimal, girls, it's again very simple, because it is 1.000 and multiply by 2's power 4. Yani I can also say 1 into 2's power minus 4. And I can say 1 over 2's power 4, which is 1 over 2's power 4 means 1 over 16. Yes, so 0.0625 in decimal. This is the way. Even you know how to convert binary to decimal to binary. You can do it yourself later on. So this is the way to convert, to perform addition in floating point. If binary is given, we have asked the result. So this is the way. Okay, it is representing 0.5. This one number. Another one is representing this one here, and this is the final answer. So I think this is the last slide, or not? Just see what's there. Okay, floating point adder hardware addition. It's about the hardware. So much more complex than the integer hardware. It's not like simple integer hardware required for this addition. It is complex. Doing it one clock cycle would take too long. If we are doing it in one clock cycle, yani do one step in one clock, second step in second clock, and so on, it will take a lot. So much longer than the integer operation. Slower clock would penalize all instructions. Yani if the clock size is very long means it is taking too much time. So because of it, the clock is slow, it will take more time, and it will also penalize another instructions which can finish early, but because of the common clock size, or which is slower, will also penalize the other instructions which can complete in short time. So floating point adder usually takes several cycles, can be pipeline. So we can have some pipeline there, any parallel operations, in order to make it fast. See the hardware for it. This is the hardware for floating point adder. So hope you can easily understand. This is 2 numbers, as I mentioned before, girls. Number 1, number 2. When we start, what was the first step? It is equivalent here. You can see the first step was we compare the exponents. Do you remember that? Then we check which one is the smallest exponent. Okay, remember. So we check first by comparing which one is the smallest one. Then we find exponent difference. How much is the exponent difference, girls? After finding the exponent difference, what do? We choose here 2 things. Yani whether we are going to use this exponent or we are going to use this exponent. See this one? It is connected on 0. This is connected on 1. So control signal will generate accordingly, and then that exponent will be taken from here as an output. So multiplexer is there. Now another one is for the fraction part. So what we said, shift smaller number right. So we took the smallest one from here. By after comparing, a result will generate, and we'll take the what is the smallest one and we bring it here. See, the smallest one is coming here. And what happening here? This is the fraction part. This is the fraction part. And for the fraction part, both are here, and the control signal will generate which fraction part we are going to take it from here. It will come down, and then we are going to shift right that one. Okay. Then we have one more mux, which is going to be controlled by the control signal, which is selecting basically here. The fraction part will be going here, or it will go after shifting actually. Because as I said, you need to adjust the decimal point. So how can we adjust the decimal point? Yani we are just shifting the number. So we need to shift this fraction one or this one in order to adjust it. So this these two marks will choose which is going to be there, right? That is it going to be direct? So direct will come here, and the one which need to be shifted will come via this route. Okay, then it will reach there. Then we will be having big ALU. Here we will be performing addition, and then after result is gonna, this is the second step, which is the addition. Yeah, it is addition is here. Third step is the normalized. So after the result you will again check, whether it is normalized or not. So this is for that. Okay, the third step is for the rounding. Then finally we are having result here. So you can understand how complicated the floating point adder hardware is. Okay, what we just explained here in these steps 1, 2, 3, 4, it is basically implemented by using this hardware, step 1, 2, 3, 4. Okay, I think this is the end of this chapter. Okay, any question, girls?
Shall we memorize all of this information?
Okay.
Which information? Okay, so your question is a good question, because you are saying 1 plus 0, 1, how it is added. As if we add 1 plus 0, 1, it is gonna be like this value, and it is not like that. So if it is not like that, what happening? Basically 0, 1 is in binary, and this is a fraction part. You do one thing, just convert this fraction into decimal. And how do we do this one? Because it is 0, it is 1, both are fraction. If I ask you write the weight of these numbers, so you will say the weight of this one is -1 because another one is -2. Conversion will be like that: 0 multiplied by 1/2 plus 1 multiplied by 1/4. Am I right now? Is it clear? I am converting fraction into decimal. Okay, so girl, then next after, when you multiply with 0, it is gonna be 0 plus 1 into 1/4. 1 into 1/4 will give you 0.25. Am I right? Which is 0.25. I am getting this answer. Okay, now, so I am representing -1 is basically -1, and this one is 1. Okay, it will be okay, just keep it out in here like that. It is 1, and we have converted this one, which is 0.25. Now it is clear?
Yes.
Okay, then multiply by 2's power 2. What is 2's power 2?
4.
4. Clear? Now, can we just complete this one? 1 plus -1.25. Is it clear? Multiply
Yes.
by 4. What you will be getting now? -5.0. Am I right?
Oh, okay.
Now clear, right?
Yes.
Okay. So very good question you raised, and hope I gave your answer and it is clear to you. All right.